Last stage, we made one GPU serve fast, paged KV cache, continuous batching, vLLM and TensorRT-LLM and NIM. But before you can serve a frontier model, somebody has to train it, and that's where one GPU stops being enough. Here's the number that ends the argument. Training a 70 billion parameter model needs about 1.1 terabytes of memory just to hold the model states. An H100 has 80 gigabytes, so you don't use one GPU. You use a room of them and make them act like one. Where does 1.1 terabytes come from? For each parameter, mixed precision Adam keeps 2 bytes of weights, 2 bytes of gradients, and 12 more bytes, momentum, variance, and a full precision master copy. That's 16 bytes per parameter. 70 billion times 16 is 1.1 terabytes. And that's before activations and the KV cache. This single number is why this whole episode exists. So you split the work, and there are only a few independent ways to do it. Split the batch. Every GPU has a full model copy and works on different examples. That's data parallel. Split each weight matrix. 4 GPUs each bolt on part of the same layer at once. That's tensor parallel. Split the layers into an assembly line. That's pipeline parallel. And split a very long sequence across workers. That's sequence and context parallel. The art is composing them. That's 3D parallelism. But two of those have a hidden rule. Tensor parallel talks constantly. Every layer it has to some partial results across GPUs. So it has to stay inside one node on the fast NVLink fabric. Push it across the slower network between nodes and throughput collapses. Pipeline and data parallel talk far less. So those are the axes you stretch across nodes. The mantra tensor parallel stays on NVLink. Pipeline and data parallel cross InfiniBand. Plain data parallel wastes memory. Every GPU stores an identical copy of the optimizer state. Zero and FSDP say, don't replicate shard. Each GPU owns one slice, gathers the rest just before it needs a layer, computes, then throws it away. And all this gathering and summing is done by NCCL, NVIDIA's collective library. Its workhorse is the ring all reduce, and the single biggest speed trick in the whole field is overlapping that communication with computation, so the GPUs never wait. Let me draw all of it on one canvas because every big training run is some recipe of these pieces. We'll build it in layers, the axis first, then the sharding, then the plumbing, then the profiler that tells you it's working. Start with the 4 axes. Data parallel, replicas in a column, one all reduce of gradients per step. Tensor parallel, one weight matrix sliced across 4 GPUs inside a node box. 2 all reduces per layer. Pipeline parallel, layer stages across node boxes, microbatches flowing as colored dots. And watch that red triangle, the bubble, the idle time we fight by adding microbatches. Sequence parallel, a long document sliced across workers. Now compose them, 3D parallelism. Tensor parallel equals 8 inside each node on NVLink. Pipeline parallel across the nodes on InfiniBand. Data parallel across the replica columns. 8 times 16 times 8 is 1024 GPUs acting as one. This is Megatron's recipe, and it's how Nematron class models get trained. Drop in 0 and FSDP. Instead of every replica holding the whole optimizer state, each owns a colored slice. The forward pass all gathers the layer's parameters just in time, computes, frees them. The backward reducer scatters the gradients. That's 0, 3. And underneath every arrow on this diagram is one NCCL collective. Ring, all reduce, all gather, reduce, scatter. All to all for the experts. One scaling trap people get wrong. Adding GPUs grows your global batch size. And a bigger batch needs a bigger learning rate, but not the same recipe. Linear scaling for plain SGD. For Adam, a gentler square root rule, roughly double the rate for 4 times the batch. And you must add learning rate warm up, ramp up over the first steps, or a large batch run blows up before it ever learns anything. Bigger batch is not a free lunch. The last piece is the perf toolbox bracketing the whole run, activation checkpointing that recomputes activations to shrink memory from order layers to order square root layers, BF16 and FP8 through the transformer engine, flash attention that never writes the giant score matrix to memory, so attention scales linearly in length, a handful of NCCL environment variables to pin the right fabric, and endsight to hunt the bubbles. That's how you train at scale. But a trained model sitting on a cluster does nothing. Next, where these GPUs physically live, how you package the model in a container, schedule it on Kubernetes, and watch it so it doesn't die at 3 in the morning. Thanks for watching. Like and subscribe for more videos like this, and I'll see you in the next one.